Thanks so much, everyone, for attending the presentation tonight, and welcome to all those online, and of course, welcome to all those in person in Hermanus. I want to talk a little bit about black holes, and I will start delving a little bit into the science behind black holes, and then I will ask the question, are these guys actually real? And then finally, I will actually ask the question, how can we find them and even image them? So let's get started. So let's for the moment pretend that the 20th century did not happen, and we just stick to classical mechanics and see how far we can get in understanding black holes just with that. And it's a bit difficult to do that via a Zoom presentation, but just imagine I had a ball in my hand and I threw it up. I mean, what would happen? It would go up, and all things that go up must come down again. So it would come down. But obviously, I could try again, throwing it with a bit more speed, and then it might reach the ceiling, and still it would come down. And then you might ask, how fast do I actually have to throw the ball so that it does not come down again? And if you do the mathematics, and I will come to that in a moment, you will get the answer. But I should point out that on the following slides, there may be a few formulas. You may deal with them by either just ignoring them. You might use the opportunity to get some well-deserved sleep. But in the unlikely event that you are allergic to formulas, please do find out where the emergency exit is now. So how fast do I have to throw up a ball so that it does not come down back to Earth? And if you do the mathematics, the answer is you have to throw it up with about 11 kilometers a second. That's pretty fast, and that is, of course, why you need a rocket to get into space. And then you might ask, okay, how fast do I actually have to throw the ball so that it leaves the solar system? Again, you plug in the numbers, and the answer is that you would have to throw the ball or anything else with 42 kilometers a second. And I tell you a bit of a secret. No technology on Earth at the moment is really able to get to that speed. But you might wonder, how on earth did we manage to get space probes like the Voyager space probes out of the solar system? And the answer is that you get some energy by almost literally bouncing off planets. So in a way, you play ping pong in the solar system, and that gives you the necessary energy to get the speed to get out of the solar system. And now you might still ask another question, which is, if I have a torch.
Just a second.
You might also ask, if I have a torch and shine light up, which goes at about 300,000 kilometers a second, well, what would the criteria be so that light actually can't escape but comes back to your body? So you can actually do that with school physics. I mean, you may remember that back in the school days, you may have learned about potential energy of the Earth, for example, and you may have learned about kinetic energy. The formulas are here on the slide. And then, of course, you can do a bit of rearranging. And then you get the formula at the bottom. And on the left-hand side, you've got the radius of a sphere. And on the right-hand side, we basically have a mass of a sphere, that's a capital M, and we have the speed of the object squared. And what this formula basically tells you is that if you have a certain speed, and if you have a certain mass combined within that radius, then the object which you throw up cannot escape. And so we can use that formula to answer the question for light. So basically, we plug in the speed of light for the speed in that formula, and that's the C here in the formula at the top. And then you can plug in the gravitational constant value, that's a capital G. You can plug in whatever mass you want. And for example, you could put in the mass of a sun, And then this formula would give you that if you combined the whole mass of the sun into a sphere with a radius of 3 kilometers, then light would not be able to escape from that sphere. Now, of course, the derivation purely classical is completely incorrect because you can't use classical mechanics if it comes to speeds near the speed of light. But by sheer coincidence, that formula actually remains correct even if you use the proper physics, which I will turn to now. So that's a piece of good luck, really. So, but let's move away from classical mechanics and ask, what is the physics behind black holes? And of course, you need Einstein, you need relativity. But let's stick for a moment with classical mechanics. One of the core ideas of classical mechanics we know from everyday life is that speeds add up. What does that mean? Imagine that you are standing on a platform and a train is moving past, say at a speed of 5 meters per second. And then on the train, there is a passenger that throws a ball in the direction of the train moving, again with a speed of 5 meters per second. Then, of course, the passenger on the train will say that the ball is flying with a speed of 5 meters per second. But you on the platform will argue that the speed is actually 10 meters per second. The 5 meters per second of a ball in the train plus the 5 meters per second of a train moving relative to you. That is, of course, how everyday life works. But if you come close to the speeds of light, things break down. And that core tenet of classical mechanics is not valid any longer. So we need something new. And so the central idea, which is new in special relativity, is that the speed of light is constant. Meaning, if you again have someone on a train shining a torch in the direction of the train, the person on the train will say that the speed of light is 300,000 kilometers per second. And in classical mechanics, you would say on the platform it's 300,000 kilometers a second plus the 5 meters per second of a train moving. But no, the speed is actually the same. So you measure 300,000 kilometers a second as well. And that may seem somewhat harmless, but the implications of that idea are actually quite dumbfounding. And to get an idea of why that is, let's consider a simple clock. And that clock basically consists of 2 mirrors and a light source. And the light source happily emits photons from the bottom mirror up to the top mirror. The photon, the light is reflected there and comes back again. And let's just assume that that takes 1 second. So it's a pretty big clock. So if the clock is at rest relative to us, then obviously you see what you see on the left-hand side. The light goes up in a straight line and comes down in a straight line, and that will take 1 second. But now let's imagine that we put this clock on a rocket, and that rocket is flying past us at a pretty fast speed. But obviously, the clock, the mirrors are moving, and now, as you can see on the right-hand side, the path the light has to travel becomes longer, simply because everything is moving. In classical mechanics, that would be no problem, because in classical mechanics, we would basically now add the speed of a rocket to get a higher speed for the light, and the time would remain the same. But in special relativity, again, the speed of light is constant. So even though the path becomes longer, the time remains the same. And what that means, of course, is that the time becomes longer now. So what takes 1 second for a guy on the rocket watching the clock may maybe take 5 seconds for us watching from the outside. So moving clocks are ticking more slowly. And that is actually something you can prove experimentally. A very famous example is high in the atmosphere, muons are created charged particles, and they have a very short lifetime. So in principle, virtually no muon should reach the ground. But indeed, what happens is, because they almost move at the speed of light, from our perspective, they age more slowly, and so they actually do manage to reach the ground in substantial numbers. So it's a very real and experimentally verified effect. As a corollary, if you do the mathematics, there is another implication. If something is moving fast past you, it will become shorter. And that leads to a nice paradox, which is known as the barn-pole paradox. So let's imagine we have a 10-meter long barn, as in this picture. And in addition, we have a 10-meter long pole. Then obviously that pole happily fits into this barn, just so. And now let's also imagine that we have a superhero. And superheroes have a habit of flying pretty fast. So let's assume that our superhero is flying almost at the speed of light. Then, with a pole, then what the farmer sees is obviously that the pole becomes much shorter, and it can easily fit into the barn. On the other hand, from the perspective of the superhero, obviously the pole remains 10 meters long, but now the barn and everything else is shortened. So now clearly, this pole does not fit into the barn. And now you can ask the question, can the farmer actually close the back and the front door with a pole inside? And of course, the farmer will say, yes, that works because it fits easily. But the superhero will say, no way, because the barn is too small. So how can we resolve that problem? Well, there is only one solution really, and that is that people moving at speed relative to each other don't agree on what happens at the same time. Simultaneity is relative. And that solves the problem, because if the farmer closes the back and the front door at the same time, the superhero will actually see that one door is closed earlier than the other. And so it all works out, weird though it may be. I know if your mind is spinning now, you clearly have deserved a break. And what better way to have a break than to watch a little video? So I brought a NASA movie clip taken live on the moon. And I do hope that you can hear the sound. Otherwise, please let me know.
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
So I hope you could see and hear that all right. So if you let a feather and a hammer drop on the moon, they both reach the ground at the same time. Everything falls with the same acceleration if there is no air resistance. And that is actually one of the fundamental principles behind Einstein's theory of general relativity. But first, why did Einstein need that theory of general relativity? Well, there was one problem with special relativity, or rather two problems. First, it really only applies if observers are moving at constant speed relative to each other. And then secondly, gravity was nowhere to be seen. And so Einstein tried to generalize his theory, and after quite a few years and quite a bit of pain, I would guess, he actually arrived at the solution. And the main idea is that he really took this notion that everything falls with the same acceleration. Doesn't really matter whether it's gold, feather, iron, whatever. And that begs the question, are maybe the effects of acceleration and gravity the same? And that is nicely illustrated by this image here on the slide, which shows an elevator with a pair of scales. And obviously, if you are standing on scales in an elevator, and the elevator is moving on upwards, your weight will increase. At the same time, if you are in a gravitational field, then of course you weigh more as well. So now, if your rocket or if your box you are standing in on the slide has no windows, there is no way for you to tell whether you are actually accelerating or whether you are actually on Earth in a gravitational field. And that is what is meant by saying that the effects of acceleration and gravity are more or less the same. And that leads to the idea that maybe gravity can actually be described as curvature of space and time. Where does the curvature come from? Maybe a hand-waving argument. If you are accelerating, say in a fast rocket, in a really fast rocket, and a ray of light was moving past your window, then obviously that light would appear bent because you are accelerating. And if the effects of gravity and acceleration are the same, that would mean that light is bent in a gravitational field as well. And it's hard to imagine something which should be straighter than a ray of light. So if the ray of even light is bent, one of the natural ways of visualizing that would be that actually space and time are curved, so that light can still move in the, so to speak, straightest line possible. So that is the idea behind general relativity. Now, obviously, you want to have a formula, you want to calculate things, and that was the difficult part. And after years, Einstein came up with a formula you can see here. And if you look at the formula, you may say that, that doesn't look too difficult. But the only reason why this formula does not look difficult is because all the problems are basically swept under the carpet in this formula. If you ask me what do all these terms mean, I will refer you to Wikipedia. And if you ask me to solve that equation, I will remind you that South Africa is a human rights-based country. It's really fiendish. I want to mention one term in particular in this equation because of the story behind it. The second term on the left-hand side has that lambda, which is known as the cosmological constant. And when Einstein originally came up with this equation, he didn't include that term. But he realized pretty soon that with his equation, the universe could not be stable. And now he actually believed that the universe is unchanging and stable. And so he solved that problem by inserting that second term of the cosmological constant. And then he was happy, the universe was stable. But then, of course, a few years later, Edwin Hubble found that the universe is nothing like that. It is actually expanding. And so Einstein dropped that term again, and he actually called it the biggest blunder of his life. But ghosts you call don't go away. And as you might know, decades later, astronomers figured out that the universe is not only expanding, but it is expanding faster and faster. It is actually accelerating. And the underlying reason is, of course, dark energy, whatever that may be, because dark energy is really another term for saying that we have no idea what it is. But if you want to describe this dark energy in the framework of Einstein's theory, you end up with a cosmological constant again. So there we go, we have it again. Now, I told you that solving this equation is difficult, but some solutions can be found. And one notable solution is for the simple case of a spherical mass, which is not rotating. And then you get this formula, and don't worry, you don't have to understand this formula. And you can actually happily ignore the second and third term on the right-hand side. But I want to highlight some things about the left side and the right side. The left side basically is the time of someone falling onto that sphere. And the first term on the right-hand side has that dt, and that is basically the time of an observer which is very far away. And then you have that term in parentheses before. And again, you have that radius rs, which we encountered earlier on one of the former slides. And the lowercase r is the radius away from the center of the mass. And what we will see is that once the radius reaches that Schwarzschild radius, as it's called, the rs, this term in parentheses vanishes. It becomes zero. So what does that mean? Even though for an observer on the outside, a significant amount of time may have passed, for the observer falling onto the mass, basically no time passes at all. And of course, once you reach that Schwarzschild radius, basically time comes to a standstill from the perspective of an outside observer. And that is actually the Schwarzschild radius, that is the event horizon. That is the point of no return. If you cross the event horizon, there is no way out again. And that really is the definition of a black hole. You have a mass which is so dense that you have a Schwarzschild radius outside the mass so that you can actually cross it. And then again, once you have crossed it, there is no way back. Now, of course, in science fiction, there are always loopholes. And I want to remember a Star Trek episode, actually from the Voyager franchise, in which they actually crossed the event horizon, but then luckily they found some gap in the event horizon and managed to sneak out again just in time. Now, even if that was possible, you have to bear in mind that your time, as seen from the outside world, has slowed down, or put it in the opposite way, the outside world, from your perspective, has really speeded up. And that means if you come close to the event horizon and then return back home, you might find no one living anymore because too much time has passed. So getting close to the event horizon is a really bad idea. So if you look at a black hole, you may distinguish between different regions. I already mentioned the event horizon, the point of no return, and that just leads, if you cross that, further and further inwards, ending up at a singularity. Well, is it really singular? Is it really infinite? One should be careful with infinities, of course, and the fact of the matter is that at the center of the black hole, at some point, quantum physics would play a role as well. And we actually don't even know how to combine the theory of general relativity and quantum physics. So what precisely is happening at the very center of a black hole is sort of anyone's guess. Then outside the event horizon, you can see that there is that dark green shaded area called the ergosphere. And that is, so to speak, the ESCOM-friendly part, because in that area, you could actually extract energy from a rotating black hole. Now, of course, all the black holes are very far away, so they won't solve our energy crisis, but at least in principle, we could use black holes as an energy source, which might make some nice science fiction stories, but not so much solve our problems here on Earth. But then importantly, you can see that at the outside there is that light green shaded area denoted the quiet region. If you are sufficiently far away from a black hole, you will not really notice any difference between a black hole and just some ordinary, say, stars. So far away from black hole, a black hole is really nothing spectacular. And that is, of course, good news, given that, as we will see, that is a massive black hole at the center of our Milky Way. It's good to know that as we are sufficiently far away, it doesn't really affect us. It really doesn't make a difference. So black holes are only really black hole-like if you get close to them. Now, talking of which, what would getting close to a black hole actually look like? And I brought a little video clip illustrating that. And of course, I don't have to tell you that the big black circle at the center is, so to speak, the inside of a black hole. So basically, the circumference of that circle is the event horizon. So let's see what happens if we fly towards the event horizon. So I start the journey now. And as we get closer and closer, obviously the black hole gets more and more prominent. And you can see that the effects of space-time curvature get more and more as well. Now we are almost at the event horizon. Almost, and now it gets really funky. And hopefully we just make it in time without falling in. And that is it. So I already mentioned that falling into a black hole might be a bad idea because there is no way out again once you have crossed the event horizon. And indeed, once you have crossed the event horizon, there's only one way, and that is basically to the center of a black hole. And the closer you get to the center, of course, the greater gravity will become. And in addition, the difference between the gravity on your feet and the gravity on your head will get more and more tidal forces. And what that, of course, means is that you're drawn apart more and more. And there is actually a technical term for that. And that effect, that dire fate, is actually known as spaghettification. And that is indeed the technical term for it. Finally, you may have heard that black holes can evaporate. That may come as a bit of a surprise because, after all, how can they evaporate if nothing can cross the event horizon? And the hand-waving explanation, and I'm never sure how well true that is, but the hand-waving explanation is, in quantum physics, we know that the vacuum is not empty. All the time, particle-anticle-particle pairs are created, but they annihilate again almost instantaneously. But now let's imagine that due to some quantum effect, a particle-antiparticle pair is created just outside the event horizon. Then one of the two might actually fall into the event horizon, and then, of course, is gone because nothing can cross the event horizon coming out again. So you're left with the other partner in the pair outside, and that is actually the radiation from a black hole, also known as the Hawking radiation. If you really want to understand that, you would have to understand quantum field theory, something I personally don't understand. Now, funnily enough, you might imagine that a big black hole is radiating more than a small black hole, but it's actually the other way around. the bigger a black hole, the less it radiates. And it takes actually very, very long for a black hole to radiate away. So I've bugged you with a lot of theory. And now you might ask the question, are these guys actually real and how do we know? And let me start with something you almost undoubtedly know. How do stars live? I mean, they start out as a gas cloud. And then obviously the gas cloud condenses, it becomes a star. The star starts to fuse hydrogen into helium. At some point, the hydrogen is depleted in the core, and then it will actually start fuse helium. It becomes a red giant, and then it goes on, and depending on the star, it may end up, say, as a carbon core afterwards, which is the case for our sun. So our sun will end its life and has finally run out of any fuel to fuse as a white dwarf. And the white dwarf is basically the same size as the Earth, but still has about the same mass of the sun. So how come? Well, why does the sun not change? And the reason is that there is an equilibrium. On the one hand, of course, there is gravity, which tries to pull the sun together. On the other hand, the sun is hot because obviously it's generating heat. And that means that there is heat pressure, which is pushing outside. And these two pressures are in equilibrium, and that is why the sun happily can stay reasonably stable for about 10 billion years. But once there is nothing to fuse anymore, there is no heat source any longer, and so the heat pressure goes away. And now gravity is winning and will actually make the sun shrink. But at some point, that will stop. And it will stop because of the electrons in the sun. Because electrons are really like visitors attending the presentation on black holes. Now, I don't know how big your hall is, how many chairs are in there, but I can imagine that if you put in, say, 10 times the number of people, there would be a lot of shuffling going on. Because people don't want to sit on the same chair with a stranger. And the same goes for electrons. Two electrons can't really be in the same location with the same properties. So if you try to squeeze electrons together, they will resist. And it is this pressure which actually keeps a white dwarf from shrinking further. And that is, as I said, the fate of our sun. I know a white dwarf is pretty dense already, but you might ask, are there denser objects? And the answer was found by Jocelyn Bell-Burnett, because she found radio signals which were completely unexpected and very regular. What did she find? Well, she did not find little green men, even though these objects originally were nicknamed LGM. What she found was, of course, a pulsar, a rotating neutron star. Well, what a neutron star? What is a neutron star? I mean, I mentioned that for the case of a sun, shrinking stops as a white dwarf because there is the electron pressure. But if you have too much mass and hence too much gravity, that electron pressure is not sufficient. So the star will still shrink until at some point you get the same pressure, but this time not from electrons, but from neutrons. So you end up with a star which is basically as dense as an atomic nucleus and mostly made of neutrons. And sometimes these stars actually happily shine a beam at us, and they are usually rotating quite fast. They are spinning quite fast. That is why you get
It seems to have frozen.
you can easily fit a neutron star into it. So you can easily fit a neutron star into Cape Town, and if I'm not entirely mistaken, if you take a spoonful of neutron star matter, it would probably be about the same mass as Table Mountain. So it's really, really dense. And now you might ask, are there objects which are even denser than this? And indeed, in the 1960s, the astronomers found such a source. They actually first found an X-ray source, and then they actually found a radio source and managed to identify that as a star. But that couldn't be the source of the X-rays, and at some point they managed to basically estimate the mass of that X-ray source, and they figured out that it is actually so massive it can't be a neutron star. Because if you have too much mass, too much gravity, even neutrons won't stop your shrinking. And by the end of 1973, astronomers in general had accepted holes. And the X-ray, of course, so X-rays basically come from the black hole, but I'm going to come to it in a moment, but they can't come from a black hole itself, because obviously nothing can leave a black hole. But what can happen is that you have matter from one star falling onto this black hole, forming an accretion disk, which really heats up, and that is the X-ray source. And if you analyze such X-ray sources very carefully, you can actually distinguish whether that accretion disk is for a neutron star or for a black hole. So now I told you that by the end of 1973, black holes had been accepted by the by the astronomy community. However, you may have heard that Stephen Hawking and Kip Thorne actually had a bet on that. And Stephen Hawking bet that black holes do not exist, or more specifically that X-ray source I mentioned, Cygnus X1, is not a black hole. Well, that is not because Stephen Hawking didn't believe it, but his argument was, I have invested so much effort into black holes. If they are not real, and if I then win this bet, at least I have gotten something out of it. And as this is a family-friendly entertainment, I will not tell you what he would have won. But of course, he didn't win. He conceded losing the bet in 1990. Now, the story of black holes could end there, but the universe has a certain habit of surprising everyone. Now, everyone was quite happy with the idea of stellar mass black holes, like the ones I have described. But astronomers actually found very bright sources in the universe. And they also found that these light sources were variable, and they could measure the time scale of variability. And they figured out that they varied at basically a time scale of a day. And that means that basically that light source, that energy source, can't be bigger than, well, one light day. And you could also estimate how much mass must be in that, well, daylight region. Why could a light day region, sorry. How can you estimate that? Well, simply because where is the energy coming from? Probably due to gravity, things falling into a gravitational field. And then you can estimate how much mass do I need. And astronomers did that, and they figured out that there is actually no way of keeping such an amount of mass stable in such a small volume. So it must collapse. So it should be another black hole. So now here, all of a sudden, you had black holes which had not the mass of a few suns, but actually might have a billion solar masses. And nowadays, we know that basically every galaxy has a massive black hole at the center, including our own Milky Way, and I will come to that in a moment. right now, actually, because here is actually an illustration of real measurements of the motion of stars at the center of our Milky Way. And if I play this video, you can see them moving, and if you analyze that motion very carefully, again, you can estimate not only the size, but also the amount of mass inside that region. And again, it must be a black hole. And that is how we figured out that at the center of our Milky Way, there must be a black hole. So that is really good, solid evidence for the black hole. Now, of course, a few years ago, another piece of evidence emerged, and in a way, a very fantastic one. Gravitational waves could be detected. Now, what is a gravitational wave? I mentioned that space and time are curved according to special relativity. And in a way, you could imagine that space and time are like a rubber plane, and if you put a mass onto the rubber plane, you will get a dent. And now imagine you have, like in this slide, you have two masses on the rubber plane, and now you start moving them around. Then clearly there will be a wave, a ripple spreading out on your rubber plane. And the same is true for space-time. If you have two objects moving around each other, you will have ripples in space and time propagating outwards, gravitational waves. Now, gravitational waves may have lots of energy. They don't have much of an effect. So it's fiendishly difficult to actually measure them. But how can you do that? Well, one way is to use interferometry. And you can see that here illustrated. So that's, of course, the technology behind gravitational wave observatories like LIGO. You basically have two arms at right angle, and you shoot light from one light source along both arms. At the end of the arm, there is a mirror which reflects the light. It comes back, and then the light which comes back is recombined and led onto a detector. Now, these arms are adjusted so that normally the light coming from arm 1 and the light coming from arm 2 would cancel out. So let me try to illustrate that by playing this movie. So you see the light goes along both arms, is recombined. And obviously, if you change the length of these arms, the light may get out of sync, and all of a sudden, it does not cancel out anymore. So here again, you first have a case where the light properly cancels out, so you get no signal. But now if a gravitational wave moves through, the length changes, and that changes differently for the two arms. And hence, they get out of sync, so to speak. The light does not cancel perfectly anymore, and you get a signal. And that is precisely how LIGO works. The idea is really straightforward. The implementation is difficult. To give you an idea of how difficult it is. So the length of the arms of LIGO is a few kilometers. The change in length caused by a gravitational wave going through is something like 10 to the negative 19 meters. And that means that the change in length of such an arm with a gravitational wave going through is about 1/10,000th of the diameter of a proton. It's absolutely amazing that you can measure something like that. The other thing I find truly amazing about LIGO is the idea for LIGO basically came up in the 1970s, and they started in earnest probably around 1980. So they managed to secure funding for decades without actually having any results to show, until they finally reproduced results which showed that there are gravitational waves. It's amazing that someone had the foresight of investing money for such a long time, just hoping that it would work out, and in the end, it did work out. And coincidentally, the frequency range of gravitational waves which can be detected by LIGO is actually basically the hearing range of the human ear. So we can basically sonify the signal. And here's actually the first signal detected by LIGO of two colliding black holes. And you can first hear it in the real frequency range, and then afterwards it has been scaled up a bit so that it's easier to hear. So let's listen to it. And you can hear this chirp sound. And then it all of a sudden stops completely, because that is when the two black holes had been collided. And now there was only one black hole, and the single black hole does not emit any gravitational waves anymore. Now, obviously, scientists always want to have more. And so just because you can detect gravitational waves in the frequency range of human hearing does not mean that you might want to detect other gravitational waves as well. For example, gravitational waves with a frequency of a few millihertz, so maybe one wave of an hour or something like that. So you can't do that on Earth, but you can do it in space. And so the proposal is to send up 3 space probes, known as LISA, whatever you pronounce it. And basically, these space probes will have a distance of about 1.5 million kilometers between them. And then they will shoot lasers between them. And if a gravitational wave goes through, then obviously, again, the length will change and things will get out of sync. And they will detect that. And even though the distance is 1 million kilometers or more, the change in length they have to measure is basically the diameter of an atomic nucleus. And it's amazing that something like that is possible. So that is the future. Now, you might ask, can we actually also measure gravitational waves which maybe have a period of a few years? And lo and behold, maybe we have discovered them already. And you would search for such graves by basically pulsar timing arrays. I mentioned that neutron stars, spinning neutron stars, pulsars are very accurate clocks. They're really stable. And so if you observe several pulsars in the sky, you could basically always see the same, right? Nothing really changing. You would have a very predictable signal. But now, obviously, if gravitational waves move through, again, lengths change. And so, in a way, the pulsar timing gets a little bit out of sync. And worldwide networks of radio telescopes have observed pulsars for something like 15 years, made careful statistical analysis, and they produced results which are at least consistent with the idea that there are gravitational waves having been seen. It's not necessarily 100% conclusive yet, but very good evidence. And of course, Meerkat does that as well. Pulsar time is one of the science cases for Meerkat, and they have done it. And amazingly enough, Meerkat was able to produce results in about 1/3 of the time of the other radio telescopes, which I think is a nice illustration of how powerful Meerkat is, and it's a nice illustration of how excellent, how world-class science and technology is actually conducted in South Africa. And then finally, all these black holes are very far away. But could it be that we are able to detect a black hole closer at home? Surprisingly enough, the answer might, and I have to emphasize, might be the case. Last year, there was a publication released which actually looked at dark matter. What is dark matter? I mean, we don't know. but we don't know that it is there because, for example, if you look at the rotation curve of galaxies, you will see that the prediction and the actual rotation curve do not match at all, as you can see on this slide. And the reason is there is dark matter, whatever it may be. And now this publication argued maybe dark matter is really made up of small primordial black holes, basically created right after the Big Bang. And then they went on to estimate what is the likelihood of such a black hole, if dark matter is made of black holes, what is the likelihood that such a black hole is actually crossing the inner solar system? And they figured out that the likelihood is that it might be that about one black hole a decade crosses the inner solar system. And surprisingly enough, of course, if a black hole like that goes through the solar system, it will slightly disturb the orbit of planets. Of course, not much, really not much, just a tiny, tiny bit. But surprisingly enough, something has frozen here. Here we go. But surprisingly enough, we can measure the distance, say, to Mars so accurately that we should be able to pick such a disturbance up. So, in principle, we might be able to see the effect of a black hole crossing the inner solar system, which would be quite fascinating, of course. But so far, I mean, I've given you good evidence for the existence of black holes, but we haven't really seen one, right? It's just indirect evidence. And now you might ask, can we actually image a black hole? Now, let me start by reminding you about light and radio waves. And as you probably know, one of the problems in astronomy is that your resolution is limited. And your resolution is limited not only by the atmosphere, it's also limited by the telescope itself, by the size of your telescope. And I've written down the formula here. You don't really have to understand it. The important bit is that if you have a very long wavelength, you will have a pretty bad resolution. That is, of course, the case for radio waves. Radio waves are really long. They are a millimeter long or even longer. And hence, even though radio dishes are pretty big, the resolution of a radio dish is really, pardon my French, crap. Now, that might sound like the end of radio astronomy, at least when it comes to resolution. But no, radio astronomers have a trick which optical astronomers can't use. They actually can combine the signals of different telescopes, even if these telescopes are spread all over the Earth. And that effectively gives you a telescope with a diameter of something like 10,000 kilometers. And now that's pretty big. And now, even though your wavelength is pretty long because your telescope is so large, all of a sudden you get a really good resolution. And you need a really good resolution to image a black hole because black holes very far away are not particularly large. So what you need is a whole network of radio telescopes spread around the Earth, as you can see here, which will observe the same object in the sky at the same time. Now you may notice on this map that there is a gap, right? A noticeable gap here in Southern Africa. Hopefully that gap will be plugged in the next years because in Namibia, the African Millimeter Telescope is to be built over the next 4 or 5 years. And then that should become part of these networks for actually seeing a black hole. And as you can see at the bottom of the slide, this whole network with common effort by radio astronomers across the world is known as the Event Horizon Telescope. Because, hey, that is what they want to see, right? The event horizon. And that is what they saw. So in 2019, we got this beautiful image of a black hole at the center of M87. And the mass of a black hole is quite amazingly large. It's about 6.5 billion solar masses. And you can see at the center, of course, the black circle, that's the black hole. So you can see the event horizon, and all the light around is, of course, an accretion disk, matter falling onto that black hole. Now, one should be a bit careful with such images. Don't be fooled. It's not a real photo, so to speak. It's actually the result of lots of measurements and lots of statistics. But the cool thing is that if you compare these images carefully with the predictions of general relativity, they are entirely consistent. So it seems that our description of black holes in terms of Einstein's theory is actually bang on the spot. Now, to give you an idea of the challenges here, the angular size of a black hole in this image on the sky is actually about the same size a credit card on the moon would have. So just imagine having to view a credit card someone left on the moon. That is how small it is. I think, again, it's one of these mind-boggling things which have become possible in the last years. Now, of course, it would be nice to have an image of the black hole near home at the center of our own Milky Way, and that is what the Event Horizon Telescope achieved in 2022. So this is actually an image of a black hole, of a 4 million solar mass black hole at the center of our Milky Way. And that is maybe as close as we can get to a black hole. That is as near as we can get to actually seeing a black hole. It's amazing that we can do it. Black holes as such are amazing. They are very real. You should stay away from them. And instead of falling to the event horizon, I hope you have a nice evening at home. And thank you very much for your attendance.
Thanks, Christian. Can you hear me?
Yes, I can hear you.
Okay, great. So we're going to try some questions. Perhaps the people who are attending on Zoom, if you'd like to maybe type a question in on the chat, that might be easier. I can just read it out. If somebody would like to ask a question, and I can maybe just repeat it so it comes onto the recording. Anybody like to fire away? Can I start? All right, I'll ask the first question. With the James Webb Telescope, have there been any new findings which have added to the knowledge about black holes specifically?
I haven't heard anything, and in a way, I would expect my study to be correct that it might be not the likeliest telescope for that because it's an infrared telescope, and I'm not sure how much black holes radiate in that region, to be honest. So I haven't heard of anything.
All right. Because, I don't know, we always seeing stuff on YouTube that, science is broken and physics has changed, all kinds of things. I think those are over-dramatized James Webb findings.
I think when it comes to that, probably a good rule of thumb is have a cup of tea and just wait for another 5 years and see what happens.
Right. Anybody else got questions on black holes? Go ahead.
What kind of radiation are we seeing? Is it gamma rays? Is it radio waves?
Okay, so Elaine's asking the accretion disk, which is falling into the black hole, what kind of radiation do we see from that? Is it gamma rays? What is it? In fact, there's something blazar. Isn't that also a type of black hole which is very bright?
Huh? A blazar, yes. Yeah, blazars are basically active kinetic nuclei, yes. Basically black holes. You can get X-rays from the hot accretion disk, but evidently you can get radio signals as well. And that is, of course, what the Event Horizon Telescope used. I detected them on the radio.
Okay, and telescopes like our SKA, the Meerkat, is that not got enough resolution to pick up images of black holes?
Yes, but while the SK I'm not sure whether they use the right wavelength range, but at the end of the day, you really want to have as big a telescope as possible. And even though the SK is really big, it does not span the whole Earth. So it would only be part of such a network, I would think.
Okay, but then is the SKA a different sort of frequency that it images compared to the Event Horizon?
I think the Event Horizon, I think the Event Horizon Telescope is.
Is that why they do?
I think it is, yeah.
Okay. Any questions? Anything from the audience on Zoom? Don't see anything in the chat.
Is it calling it a black hole or whatever? It will be a black mass.
Is it a misnomer to call it a black hole? Should it be a black mass?
Well, what's the name, right? I think in a way I would argue that it's not so much of a misnomer, because I think the intuitive idea of a hole is that you fall into and that you can't climb out again. There are people who might call it different things, like there's one popular scientist who rather preferred the name shining mountains of light, something like, because of a bright accretion disk. Black mass, I think in a way, if I heard the term black mass, I would just imagine that it's just normal mass. But at the end of the day, it's a name, right?
Okay. And I ask another question. A smaller black hole with a small event horizon has a very high density of mass within its radius. If you have a much bigger black hole, the ones like billions, the actual density within the event horizon, or the matter, the volume divided by the matter in it, the mass in it, is actually lower. So the bigger, is that correct? Because
no, that is not.
The volume
increases
by the cube and the radius increases by the square mass.
Not quite, because you would assume that basically all the mass inside the event horizon basically has collapsed into a point.
But the total
So
mass
it's not that.
in a bigger radius black hole is less for the volume than a smaller one. If you just use
it's just that you don't. Yes,
simple sort of Newtonian type of formula. So
if
what
it was
I'm
a simple
trying to get
Newtonian
to,
type, then yes.
if you take the whole observable universe, the total mass within it, it's not enough to make a black hole for the radius of the observable universe. But if you go about a third of the radius outside that, then the density of the observable universe is enough to be inside a black hole, isn't it?
I'm not convinced.
Tell me I'm talking rubbish or not.
What would have to do with numbers, but I would be a bit surprised, because you really have to have a very dense mass. But I may be wrong. I stand to be corrected.
So, I mean, we don't have doctorates in physics, and we see these YouTube videos. So if you do this calculation, then the universe could be in a black hole, and so what it tells me, if that is possible, just mathematically, then the interior of a black hole could be no different actually than the exterior of a black hole, possibly. And well, okay, it's supposed to all be within all the mass is supposed to be in a vanishingly small point in the middle. But
Yeah.
has the theory about
No,
that
well, I
changed?
think what is true is that if you have a really big black hole, right, cosmic event horizon might not seem to be much of an effect for you. That's true.
Anyway, it's all speculation. I'm not going to dive into a black hole.
One more question.
One more question.
If the black hole is like a plug hole at the sink path, and everything's flowing inside it, going down to the bottom, where does it come out? Does it come out in another universe?
Okay, no, well, that's the person is asking if the black hole is like a plug in a sinkhole and everything's flowing into it. Where does it come out? But I think that is really a two-dimensional visualization of a three-dimensional thing. So the black hole, everything flows into the interior from all sides of the black hole. Really, it doesn't really flow up.
Well, there is of course the idea about what happens if you join two black holes in a way, right, to form a wormhole.
Yeah.
So in principle, I think you could have something like a wormhole for traveling from one part in space quickly to another part in space, as you know from science fiction movies. Whether they are real wormholes, A, we don't know. B, we have no way of stabilizing them. So it would be a bad idea to use them. I don't think that you would create a new universe inside a black hole, though, to be honest.
Okay, so it's science fiction. Let's leave it at that. Okay, sorry, next question. Go ahead. I couldn't hear the question.
Atmosphere. Is there an atmosphere around the black hole?
Is there an atmosphere around a black hole? In a sense, there is, because you've got the accretion material revolving around it. I suppose we could call that.
If there is an accretion disk, yes.
If there is an accretion. And the physics of a spinning black hole, is that very different? Would the mathematics be completely different? Working things out?
I mean, in principle, the equations would be similar, I guess, but the mathematics becomes even more fiendish. I think there are solutions for rotating black holes, but that is when it gets really, really difficult.
Yes.
But you can do it. I mean, in particular, numerically.
All right. Okay. All right. Sorry, we're reaching the end of our session. So we'd like to thank you very much for everything. And fantastic, very detailed presentation. Thank you very much. Can we give you a clap?
Thank you.
So I wasn't able to tell you, but we were talking just before you were talking about Cape Town and so on. There was a break in our link, but it just carried on again afterwards. But I will join everything into a video and I will upload it to YouTube and I'll send you the link. All right. So once again, thanks very much. We hope to see you again in the future. Thanks, Christian.
Thank you.
Okay.
Bye. Have a nice evening.
Thank you.